yeah, today, the 7 deadly myths of solar. That's what we're up for. So let's just see what we can cover. Now, I'm waiting for a few people to arrive and making sure that the stream's all working properly. So just give me a moment while we let people roll on in. Yeah, okay, so it looks like it's working. I've got a feed coming in on my phone, so that's how I decided is the best way to make sure that I'm not looking at the wrong thing, and that I can actually see that this stream is in fact working. So that's good to know. All right, everyone. So with no further ado, I'm going to get into the 7 deadly myths of solar. Now, this is a presentation that I've given some time ago. It was really spurred on by Matthew Wright, who some of you may know formerly from Beyond Zero. He pointed out to me that there's a lot of things that are holding back solar, and that these are kind of effectively myths that people are hanging on to, things they think you can't do. And so I'm just going to address these directly as 7 different elements that you should consider. Some of them you'll probably quite familiar with, others might take a bit of explanation. And some of them often think that these myths are illegal things that you can't do, not just a bad idea, but illegal. But I'm going to break them down and explain how they actually are perfectly okay. So let's jump into it. So we've got the 7 deadly myths here. Now, I did base this presentation originally on Mythbusters, and hence I tried to dress up as Jamie from Mythbusters. Didn't do a very good job with the beard, but anyway, the beret. And I forgot to iron my shirt, but anyway, there you go. So the things I'll cover is parallel strings on a single tracker, oversizing PV power, inverter input current limits, south-facing arrays, shading. Is it bad? Is it good? Well, does it matter? What, is west really the best? And what is the optimum tilt angle for a PV array? So, first up, the old east-west array question, which never seems to go away, this one. It's amazing how persistent this is in terms of people's understanding of how PV works. So one of the things to consider with PV is that the voltage on a string determines, the combination of voltage and current determines how the maximum power point tracker is going to work. And if you've got 2 strings in parallel connected to a single maximum power point tracker, what's going to be the impact of those 2 strings in parallel? And do they actually need to be on the same roof and facing the same direction? Now, there is a kind of a confusion around a clause in 5033 which says all modules in a string must face the same direction and inclination, plus or minus 5 degrees. But the definition of a string is a series connection of modules, not a series and parallel connection. So you can have multiple strings at different orientations and different inclinations and parallel them. But there are a few provisos. The voltage must be within 5% as well of each of those strings. And that effectively means you're going to have the same number of panels on each string. There's a good reason for it. And I'm going to sort of try my best to explain this with a drawing. So let me just bring that up. Hang on. Here we go. Yeah, I've got this little drawing pad over here, and see how this works. I'll switch over to it, and I can talk to you, and I can draw. All right, so here I am at the drawing station. So let's do a aerial view or plan view of a roof. So here's a roof, and we'll make it a hip roof like this. And the customer wants the usual 6.6 kilowatts. It seems to be a magic number. So we try to stick a bunch of panels on this face of the roof, but you can't fit the whole array. and we're going to stick another bunch of panels on this face of the roof. Now let's just say the direction of north happens to be here. Now it actually doesn't matter. This rule applies to whether you're facing the array's mismatches in any direction. It doesn't have to be opposite. It could be north and west, and north and south, etc. So over here we've got east and we've got west, and we've got a bunch of modules sitting on the roof here. So what I'm going to do is connect these not to a dual MPP tracker, but to a single MPP tracker. Now your first question might be, why, Glenn? Why bother? Well, it just might be what you've got. It might be what's available. And the way we're going to connect it is parallel these two strings together. So I'm just doing it as a single line diagram. So we're paralleling them and bringing them down to the inverter. So that's got one MPPT at the inverter. So MPPT is here. Now you might think, well, that's all very well, Glenn. You've got the same number of panels. So in this case, we've got 8 modules on the eastern side, and we've got 8 modules on the western side. So we've met the requirement to have the same number of modules in each string, but have we really done a good job here? Because what's going to happen when the sun comes up in the morning? And so the sun comes up in the morning. I'll just put over here. There's our sun shining nicely. It's going to really pound in on that eastern array. Now, I just realised yellow's not the greatest colour. Let's make it a really super bright pinky colour sun. Here we go. It's a pinky colour sun. And that's shining in on those modules on the eastern side. Now, we know that the characteristic of a PV module is that as you increase a radiance, you increase its voltage, its VMP. So one of the things that happens as a radiance increases, so a radiance, the power of the sun, as it increases, VMP, the voltage at maximum point, increases. Right, so that would make you think that we're going to get different voltages on these two strings because, of course, the strings on the western side are not in full sun. Over here, they're in partial sun. So if I was to get a clamp meter out and stick it around here and stick it around here and measure the current, I would see a big difference in each of those strings. Let's say I'm measuring the current here at, say, 8 amps, and over here, 2 amps. Okay, so I'm getting a big difference in current and therefore power in the two strings. That's okay, but what we are told that we've got to have the same voltage in both strings. So you would assume that the panels on the western side, which are not truly in shade, they're in what you would call partial or low irradiance. They're in low irradiance. So as irradiance goes down, okay, irradiance goes down, VMP goes down. And so you'd think, oh, that's not good because that means the voltage is lower on the western side of this array. But there's a happy bit of physics. Now, this is not anything engineered into the panel deliberately, it's just the way they work. And it's to do with how VMP is affected by temperature. So as you increase temperature, as the temp goes up, the VMP, I didn't do a very good job there, VMP goes down. So what do you know? As the temperature goes up, VMP goes down. So that means that the effect of temperature on VMP counteracts the effect of irradiance on VMP when there's a difference between these two strings. So the panels on the eastern side are hot, which means that they're derating on voltage, but they're in full irradiance, which increases the voltage. So the two things kind of balance out. And it just so happens it's true on the other side of the roof where the panels are cool, so their voltage goes up. And because they're in lower radiance, their voltage goes down, and the two things counteract each other. So you might think, well, that's all very well, Glenn, but why not you just use a dual MPPT inverter anyway? Surely it's better. Well, yeah, I guess you're right. The industry has kind of come across to that one and say that, multiple MPPTs are a great idea. They make life easier. It gives you the ability to have dissimilar numbers of panels in each of your strings. But if you do have this situation, and actually it is more common in commercial systems where you have large numbers of panels with large numbers of strings paralleled at the inverter. So as long as all the strings are the same number of panels, it doesn't matter which way they face. Now there is a big proviso here in terms of performance. Now you might think, well, it's all very well, you can do it, it's allowed, the manufacturer allows it, the standards allow it, but surely you're going to degrade performance somewhat. You'll be able to squeeze a few more watts out of each string if you use 2 MPPTs. So both SMA and Fronius have produced academic papers and have studied this phenomena and shown that there is very, very, very small difference, less than 1% benefit in having a dual MPPT if both arrays are equally unshaded. So there's a difference between lower radiance and shade, because shade's localized, so like a tree shading over one panel, for instance. So as long as there's no nasty big trees, so if we did have a nasty big tree that in the morning shaded one end of this array, that would not be a good thing. That would definitely have an impact on the performance of the system, because now you would get dissimilar voltages in the strings and the tracker wouldn't work quite so smoothly. But as long as that's not true, if there's no localized shading on one of those strings, it'll work just fine. So there you go. East-west arrays, you can do it. They do work. It doesn't have to be east and west. It can be north, south, north, east, any combination you like, as long as the strings are the same number of panels, the same technology. So there you go. So that was kind of a slightly longer than 2 Minute Tuesdays answer to that particular myth. So let's just jump back into my second myth, which is, where are we? Oh, hang on. I even referenced the standard. That's right. I forgot I made this slide, but there you go. I just referenced AS 5033. ASNZ is 5033, and the 2 conditions that have to be met. So there you go. Next one, oversizing. Now, gosh, this one gives me so much grief. Let me tell you a story, everybody. You're all sitting down, comfortable, got a nice warm drink or a cool drink in your hands. Now, once upon a time, long, long ago, I used to be involved with writing the design guidelines for the Clean Energy Council. And in those design guidelines, they were non-mandatory back then, so there was no CER requirements for compliance. In fact, the CER didn't even exist. But we wrote those guidelines as a best practice guide to help the solar industry do their best. And one of the things that we put in that was that the AC output power of an inverter should be at least 80% of the peak watts of the array. Now, we put that in there as a rule of thumb. In fact, the words were, as a rule of thumb. Now, that then in revision of the guidelines became 75%. So the AC output power at least 75% of the peak watts of the array. And the rationale behind that was that solar panels way back then were very expensive, and we didn't want to kind of waste any watts. It was a very kind of precious approach to solar. Every watt counts, and you can't let any of them spill, not be produced and turned into AC power. So it wasn't a safety issue. It wasn't actually a performance issue. It was just getting a maximum yield from your array. Unfortunately, the way the STCs go is that you have to comply with the CEC guidelines, which effectively makes them a rule, and that rule is for grid connect systems without batteries, and note the word without is in bold, that you cannot exceed that ratio. So even though the wording is 75% AC output power of the peak watts of the array, if you do the inverse of that, it's 133.3% recurring PV power greater than the inverter power. So the old 133% rule is back, and it's enforced, but it's only for grid connect systems without batteries and only for systems that create STCs. So there is another option, which is if you have energy storage, it don't apply. This rule does not apply, but other rules do, which is, as always, the manufacturer's recommendation. So check with the manufacturer what the maximum oversizing ratio is. Some of them are very, very big. Like there will be current limits on the MPPT, but in terms of power limits, they may be able to handle and throttle back the inverter even when it's got twice its rated AC output power in PV modules connected, what the so-called DC power. So you see some very high ratios, even higher than 200%. So there's no practical problems, but you just need to follow the manufacturer's recommendation. And the reason that oversizing has become very popular is certainly in Australia, where the only rebate is on solar panels, and it's still very generous. It means that oversizing actually keeps the cost of the system down. When you've got STC values more or less covering the cost of modules, but not the balance of system or the inverter or the labour, then you actually want to put as much solar on that inverter as you can. But from the customer's perspective, it means that I've drawn a picture there of a perfect sunny day. Every day isn't like that. So when you've got a day that's not perfect, the more modules you have, the more likely you are to produce more usable energy for the customer. So oversizing, not theoretically a problem. It really helps with getting the maximum amount of renewable energy to the customer. So I'm looking around to see if there's any questions come in, and this they have. Oh gosh, I'm using a new rig here, so I'm just getting my head around how it all works. And so where are the tips for today? That's why I typed that in. The ad scared the shit out of me. Oh, really? And Stephen asked, orientating solar panels to minimize power shortfall. Very, very good point, Stephen. So once upon a time, everything isn't a children's story here, but it sounds like it sometimes. The idea was to produce as much energy as you could and try and export all of that energy out to the grid. And so we were seeing systems trying to face them all north, if possible. And if the poor customer had a house that faced east and west, and you'd see all these tilt arrays stuck up on the east and western side of the house trying to face the panels north to get the most amount of export. And that was because there were incentives for export. When the price for electricity exported is greater than the price that you purchase it at, then it makes sense to export it. But those days are gone in Australia. We don't have healthy export incentives for solar. It's all about self-use. And once you start talking about self-use, you've really got to look at the customer's load profile. When do they use energy? And that has a big impact on what is the optimum array configuration. So actually I'm going to do another drawing for this one. So I'll just cut across to my little drawing pad and get a nice fresh sheet of paper out. Here we go. So this is a pretty typical load profile for a residential customer who goes to work during the day. So that might be 7 a.m. here, and that might be 7 p.m. there. So that's a fairly typical profile. And then we apply a sunny day to that. And what do you know in terms of power? Sunny day. That's a perfect sunny day, like every day in Queensland. And so this is power along this axis here. Now, unfortunately, everything above the load line, so the black line is load and the pink line is solar, is going to be exported. So at a lower rate than they purchase electricity at. So it makes a lot of sense to try and move that peak towards either end of the day. Now, as a very simple way of doing that without energy storage is to actually orientate the array to east and west. You might even put a few more panels on the west, because of the afternoon, as the panels are more perpendicular to the setting sun, the performance will be more skewed to the west. So I'll try and choose a different colour. If we had east-west array, we'd get 2 bumps. But they wouldn't be as big, but they'd be earlier with a long tail. So that would be our east facing array, east PV. So it depends on the time of year, of course. And this would be our west PV. Oops, wrong end of the pen. That's the super fine end. So there we go. So that would be the western PV array. And you'll see that we're now getting better coverage into the late part of the day. Now, the other thing is season as well. In summertime in southern states like South Australia and Victoria, the sun gets to very low angles very late in the day. In fact, it goes through in midsummer nearly 270 degrees from sunrise to sunset. So actually in summertime, the sun doesn't rise in the east, it rises in the southeast. And it sets in the southwest. And what do you know? That's often when people, certainly in the afternoon, are turning on their aircon. And the aircon is really pumping in late afternoon, and the sun's still up, and it's gone past the north side of the house. It's around towards the western side of the house. And so it makes a lot of sense to try and orientate an array to pick up that late part of the day energy to maximise self-consumption. Now, of course, if you've got batteries and they're big enough, that will help too, because it will be able to store that peak during the middle of the day and release it later. But really, design sometimes is cheaper than adding hardware. So, batteries still are quite expensive and don't necessarily, the return on investment may not yet be there if you just want to maximise self-consumption of solar. So thanks, Stephen. That's a good one. Okay, so someone's asking, is Kane Thornton watching? I'm not sure what that refers to. I'm not bagging the CEC, by the way. Like, I helped write those guidelines back in the day when they were just a best practice guide, and they've kind of got locked in there. With batteries, you can sort of sidestep them, but there you go. They are what they are. Or you can choose not to be part of the small-scale technology scheme and don't create STCs. No, I don't think anyone's going to do that one. It's hard to give up on that incentive program. So let's move to another myth, and I'll bring it up. Okay, inverters have an input current limit. Now, some people see that as a maximum that you can connect to the inverter. So if it says the maximum input current is 10 amps, you might go, oh, well, at 11 amps it'll just blow up, or 12 or 15 amps it'll just blow up. But you've got to understand there are actually different reasons for the way that limit works. There's the point at which the inverter determines when to not operate the array at its maximum efficiency. An inverter actually is a smart load. It determines the amount of power to pull from the array. And it does this by adjusting the maximum power point tracking point. Now, I love drawing, so I'm going to draw another picture. Just got to cut back to my pictures. Here we go. So let's look at a IV curve of a solar module or a solar array, and it's characterized by having a bit of a knee. So here we've got current, and here we've got voltage, and the point at which the sum of current and voltage give us the maximum power is what we call our maximum power point. So MPP, and a device that tracks that is called an MPPT, a maximum power point tracker. So if I was to draw on another axis, the power output of this system here, so this is power, we would find that the power peaks at a certain voltage and current. So here we've got our voltage maximum power, and here we've got our current at maximum power. So that's short circuit current, and that's open circuit voltage. So that point is where we want to hit all day long, and that's the role of a maximum power point tracker. It deliberately adjusts the voltage and current of the array to get the most power out of it at any time. But let's say you've oversized your PV array and it's capable of producing more current than the inverter can convert. What will happen is it will just move away from the maximum power point to control the current. So it may choose to operate at a false MPPP. So we'll call this one a false MPPP, maximum power point. It's not a maximum, so hence it's false. And so by raising the voltage, and it does that by impedance, because the input impedance of the inverter's DC input determines the amount of current that will flow, limits that current. So this is a long-winded way of saying that inverters actually operate the array to draw the current they want to produce the power they need. And if they reach their manufactured limits or their thermal limits or their hardware limits, they will throttle back that. But there is another consideration. It's known as the maximum current in case of short circuit, and that often relates to the plugs and sockets on the inverter itself. So the manufacturer will give you some guidance on this. They'll say what the maximum short circuit current of the inverter is, and they'll give the maximum operating current of the inverter. As long as you don't exceed the short circuit current, you can, by design, actually have an array that produces more operating current, but it won't actually be produced. It'll be throttled by the inverter. So there you go. That's myth number 3. Inverters will blow up if you put too many panels on them. Well, actually, if you put too much voltage on them, they'll definitely blow up, but not because of current, because they control that. Okay, let's bring up the next one. Gosh, I can't believe how long this one's been around for, this myth. South-facing arrays. South-facing arrays, I've heard people say they don't work. They're illegal. You can't create STCs because they're not facing an ideal direction. In fact, they're facing probably the worst direction. Actually, the worst direction will be vertical south, just a wall. Well, it's not. None of those things are true. The requirements for creating STCs are actually quite humble. The system just needs to be capable of generating electricity, installed by a CEC accredited installer, and needs to be installed to Australian standards and CEC guidelines. You tick all those boxes, and you realise the only performance requirement to create STCs is it's capable of generating electricity. I sometimes jokingly say you could install it in a garage so that one day a year a beam of sunlight comes through a window, hits it and turns it on. In fact, it only has to do it the day you install it. There's no requirement that it does it thereafter. So it's a pretty low bar, and you might say, well, that's just wrong. It doesn't make sense. It's not good for the environment. But it is just the way the regulations were written. So without a rewrite of the scheme, the small-scale technology scheme, that's really not going to happen. It is what it is. So even though you're allowed to do it, why would you bother doing it? Well, this is where it does get really quite bizarre. People assume that south is always bad, but it's actually about where you live on the planet makes the difference. And then the closer to the equator you live, generally the better the yield, though clouds become a problem around coastal areas. So inland, close to the equator, gives you the maximum performance of a PV system. If you use just some solar radiation tables for Australia, for instance, and do averaging across the year, you'll find that the northern states like Queensland are pretty good, or very good, and as you get down towards Melbourne, lower, and Tasmania, a little bit lower. So, yeah, there's a difference where you live, but imagine you put a south-facing array in Brisbane. Is it really that bad? Well, looking at the modelling, it's about as good as a north-facing array in Melbourne. So if you can't put a south-facing array on a roof in Brisbane, you shouldn't even be able to put a north-facing array on a roof in Melbourne, because it's just the same. So there you go. There's no reason you can't do it. But why would you bother? Well, it's always a good idea to look at the design holistically. And as Stephen pointed out in the comments, in the chat, think about your orientation based on the customer's requirements. So if they need energy at certain times of the day, that's going to be a more important factor. But then again, there just may be no room anywhere else. So, system upgrades, the plumber got there first and put the hot water panels on the north side. All of those reasons can lead to it's just not going to fit on the north or the east, and you'll have to put it on the south. Now, I've actually put a south-facing array at about 15 degrees inclination, so facing south 15 degrees from horizontal, on my neighbour's house here at the at Burumara Co-op where I live, which is also where the Smart Energy Lab is. And I made a little mistake, which is you've got to allow for the length of shadows of anything to the north. And there was another array on tilts to the north of the south-facing array. And what do you know, for about 2 weeks of the year, there's a shade line across the array, just enough to turn it off. But that's not a big problem because this house is on a microgrid at our place, so everyone shares energy, so kind of doesn't matter if one house is doing a bit less than another. So there you go, that's south-facing arrays. Yes, you can do it. Keep those comments coming and those questions. It's nice to know that some people are engaged, and I hope to address some of your specific questions. So let's go back to my slides here. So shading of an array is bad. This picture I've had for a long time. You've probably seen it before if you've been to any of my talks. It's actually, I think it was a library or a public building or council building. Yeah, they obviously didn't really worry about performance. Those panels are completely under a tree. There's a lot of dust and shade. But the other thing is they face almost every combination of directions, and I'd hate to think what the stringing of this system is. It's almost like someone flicked a pack of cards onto the roof and wired it up. But shading doesn't automatically mean that it's no good. There are ways to mitigate against that. Having longer strings with higher voltages and higher in the MPPT range of the inverter is one, because you will lose due to bypass diodes causing the shaded module to be bypassed. You'll lose its contribution in terms of voltage to the string. So if you have got just enough voltage on a hot day to turn the inverter on with all the panels working and one of them gets shaded, the inverter may shut down. These days it's not such a problem because we generally are trying to max out our inverters and put a lot of panels on them. So it's not a big deal to have a bit of shading, and if it's intermittent like a chimney or so, you can live with it. But be aware that not all modules are rated for continuous bypass. So if they're permanently in shade for long periods of time, such as a panel behind a chimney, which every day for 4 or 5 hours is in shade, those bypass diodes can get pretty hot, and they may not last the distance. A bit more effective solution is to have module level power electronics. So if you've got shading, using either microinverters or DC-DC PCUs, power conditioning units, commonly referred to as optimizers, brands like Solar Edge Optimizer, Tego, Huawei. They all work by making each module operate independently of every other module, even though they're in a common string. So they've got a way of optimizing for shading, for module mismatch, for temperature, even for different types of modules. So they don't all have to be the same. So that's a great way to deal with shading. So you can still create STCs even if you've got a shaded site like this. West is best. Now this kind of is a variant on where we talked about orientation and performance. There's been all sorts of claims about which is the right way to face a solar panel. Things like you should face it north, you should face them east and west. Oh, no, west is best because that's when power prices are high and it's hot in the afternoon in many states in Australia in summertime, and you want to get the most performance. But really it's all about looking at the customer's requirement. So there's no simple rules on what's the best orientation. Do they have storage or not? All of those things can be considered. But I have seen some claims that certainly once we get high penetration of PV, we already do, that orientation can have an impact on the grid, such as high grid volts, and that may well be the time when inverters start to ramp down their performance because of the requirements now of DNSPs, your network service providers, to have the volt var functionality enabled and the volt watt, which basically means that as the grid voltage starts to climb beyond certain limits, that your inverter either exports reactive power predominantly, which doesn't give you any income, and reduces the amount of active power, and therefore not increasing grid voltage, or it actually just decreases the power of the inverter altogether, and therefore doesn't impact on the grid voltage. Another thing to consider is thermal losses will be greater later in the afternoon, so west may well mean the panels are running at the hottest time of the day, and therefore their performance will be somewhat degraded. All right, so we've got another comment in here. Should I wear a tinfoil hat with the Huawei PCUs? Well, I'm not into brand bashing. I've got a couple of Huawei inverters here, and I'm pretty confident that's what all they do. They don't seem to be monitoring me in any special way, but they are in a shed, which is kind of like a giant tinfoil hat. The Huawei, since you mentioned Huawei, the Huawei PCUs are a little bit different than both the SolarEdge and the Tigo ones in that they can be either used in complete deployment. That means every module has one. And if you have a Huawei optimizer on every module, you now have the ability to add the Safety C box, which is a little device that allows you to turn off every module at the inverter, basically with a button. So it gives you the sort of the safety requirements that are standard in the US now with Safety C. But you can also deploy those Huawei inverters in partial deployment, so they'll only optimize the panels they're on. You don't have the ability to shut down the array with partial deployment, but you can use them similar to Tigo as just put them on the problem modules, really. So that's quite interesting. We've got a few more questions here. Abhishek. G'day, Abhishek. What is your rough estimate of the efficiency of optimizers from manufacturers, options like SMAs, shade fix? I haven't done any technical studies of the efficiency benefits of optimizers. I think there's lots of reasons that you might use them. Efficiency might be one of them. I don't know if it's an overriding reason because the cost of PV being low, and when you consider the cost of additional equipment to get more efficiency, it may not be justified. A bit like once upon a time we used to tilt panels to the optimum tilt angle, even when the roof faced north. It just doesn't make sense anymore from an economic perspective because the cost of tilts is similar to just adding more panels, and you get rebates on panels, not on tilts. The same could be said of optimizers. You don't get rebates on optimizers, but you do on panels. But then again, you may need those other features such as shade and tolerance and Safety C, and so they could be some compelling reasons. So lots of reasons that optimizers are part of the market. Sam says the government isn't listening to our thoughts. Sam, you might have to articulate that thought. I'm not sure if it's the PCU question, but keep those comments and reactions coming in. Thanks. All right. Where are we? I'm on the wrong screen. One more. Last one in the 2 Minute Tuesday. You might think that I'm a bit long-winded for 2 minutes. I guess I was trying to say I was going to do a bunch of short, punchy points rather than one long single focus. So this one here is about what is the optimum tilt angle. And you can do it from lots of different methodologies. If you're trying to get, say, a solar farm, it's about the yield of the farm. And something interesting lately has been, I've noticed, is that tracking systems have really come back. I used to bag out tracking back in the day because it was expensive and unreliable, and it was mainly like small, on a small PV system, 5 to 10 panels with a tracker. And the cost of the tracker just didn't justify all the reliability problems of the tracker itself, even though it may have given you quite a bit more yield. Then we started to get some good arguments for them when they had high feed-in tariffs, and you were limited by inverter power, not by kilowatt hours per day generation. So there were 10 kilowatt trackers out there that were, or even bigger, that were connected to inverters to get maximum yield and maximum export. So that was a kind of market stimulation for trackers. But now what we've seen in large-scale solar is it's about the cost of land. Land is valuable and precious, and to get the maximum yield from that land, trackers really help. So we're seeing tracking come back in a big way for large scale. But what about fixed arrays? What is the optimum angle? It once again is all about understanding the requirements of the customer, but then it can come down to practical things. Here's a picture of an array perfectly flat on a roof. Now, flat is not the optimum unless you happen to live in the tropics, above the Tropic of Capricorn or Cancer, in that zone, the tropical zone, where flat will work very well. But you've still got a big problem, which is dust and dirt. Dust and dirt collects very well as on flat panels, particularly modules with frames. And so the framed array is going to cause a significant degradation of that performance due to dust collecting. In fact, the frame acts like a little swimming pool and captures the water and the dust, and as the water evaporates, it leaves behind the dust. So you get like little circular muddy puddles in the middle of your modules after a while. That can be overcome by cleaning. You might go, well, that's labour, but then again, in some applications, it's just a standard part of maintenance on a system is cleaning them. You may live in an area with high rainfall and low dust, or you could use modules that have no frame. So frameless modules are much better at draining dirt and dust away. And there's even nano coatings for modules that repel dust. They're pretty amazing. You put a drop of water on them and it just runs away, just runs straight off the panel. So yeah, flat, you think, well, it can be done, but why? Well, actually you cover the roof more fully. So you're actually getting no gaps between modules, no inter-row spacing, and getting a lot more coverage. For those of you from South Australia, you may have seen the showgrounds. I visited it probably 10 years ago. I think there's like 16,000 modules all flat on the showgrounds roof. And everyone, when they see those pictures, goes, yeah, but how are you going to fix it? And I just smile and go, well, it's electrical work, guys. Someone's got to be paid for it. So, yeah, it can be a big deal if you get a module in the middle of a massive array that's failed. Even finding it could be a problem. But, yep, it does give the best coverage. But there is another side benefit that not initially considered. Architects are starting to cotton onto it, which is the benefit of shading the roof. You've now got a false roof above the actual roof of the building, and you're stopping direct irradiance onto the actual roof. The panels themselves with that air gap between them mean they'll moderate the temperature, stopping direct impingement of solar energy onto the space that's going to be heated inside the building, and that can have quite a big impact. I'm trying to remember the numbers, but I think they found several degrees, like maybe it was about 5 degrees drop on that showgrounds in South Australia in summertime because of the array. So that's just the shading benefit. And that then correlates to, if it's an air-conditioned space, saving on energy. So I've got a few more there. Stephen says, Shade Fix. I always thought it was created by SMA marketing department, as I'm sure it used to be called OptiFlex. Isn't it just the MPPT IV curve continually being adjusted? Actually, to be fully honest, I haven't looked at Shade Fix. It does sound like one of those full sweep IV curve algorithms, which is to try and find the true maximum power point when there is any localized shading. Now, I might actually cut across to my drawing pad to explain this one. This is the last one in these drawing sequence. So when you've got a perfect array, as I've just drew before there, and you get that lovely IV curve that's smooth with the knee that drops off, and so it's pretty easy to know that that's the point that you want to hit. And how does the tracker find that point? Well, it does it by this thing called perturb and observe. It's a kind of technical term for just change stuff and see what happens. So this is what happens, is the inverter starts at open circuit in the morning because it's waiting for the sun to come up, and as it starts to see a voltage that's useful, it then lowers its input impedance, draws more current. So it starts tracking along this line, slowly lowering its voltage at the same time increasing the current it's drawing from the array. But it does a little sum. It goes volts times amps equals power. Did I get more? Each time I changed the operating point, did I get more power? And at some point it goes, yep, I got more power. And then it goes, no, I got less power. So it turns around and goes back the other way. And that's one of the reasons, if you've ever looked at the voltage window or the voltage maximum power point of an inverter, it's never static. It doesn't sit there on 437 volts all day long. It'll be just darting about. So that dynamic methodology is very effective at finding the maximum power point unless you've got partial shading. And when you have partial shading, you don't get a nice perfect line like this. You get a bumpy one. You get one that looks like this. And so you end up with effectively two knees on the curve. And the problem is, which is the right one? Well, using the normal methodology of just tracking along till you find the best spot from the highest voltage going downwards, you'll stop at, this is called the local MPP. So this point here is actually not the best sum of voltage and current, but it will never actually get to the global, which is up here, the global MPP, because it's doing that turnaround at the local. And what those systems, such as, I presume it's OptiFlex does this, shadow sweep, I think solar, what's the New Zealand company that makes it, or used to make inverters, had their own algorithm too, that was kind of optimized for New Zealand conditions. But really this is saying if you have cloud and or localized shading, you may not be operating at the global MPP. You may be stuck at the local one unless you do a full sweep of the curve. So the process then is every so often, they don't do it continuously, they'll go and sweep the whole curve all the way across, and they'll go, bing, I found the right spot. It's here. It's not way back there at the local MPP. So that's what those systems are used for, is to overcome a misdiagnosis of what is the best operating point of the array. Okay, here we go. So, that was the theory for today, and I kind of aimed to go for about an hour, so I got about another 15 minutes. And I wanted to bring in some fun stuff. And the fun stuff is, I call it the good, the bad, and the ugly. For those old enough to remember that movie. So some of this stuff is pure crap solar. Some of it's not so bad, and some of it's actually quite good. So what I've done is just given a little run through on some systems that I've given it the tick of good. And some of these are really quite old. This one, I took this picture probably over 10 years ago of a system in Queensland, and hats off to the installer. Not is only the workmanship really well done, but some really clever design features. Now, for those of you familiar with the Sunny Island inverters, with those SMCs, the red ones, and Sunny Islands, the yellow ones, so it's an AC coupled system, about 30 kilowatts, I think, of solar. But this is in the tropics, or not really, it's just not out of Brisbane actually, Moreton Island. And so it gets pretty hot in summertime, and that's a sort of dedicated building. And so it would get pretty hot even though it's under palm trees. So you'd think it would need ventilation, because inverters actually give out heat, particularly, battery inverters at around sort of low 90s. There's a fair bit of heat being given off from them when they're cranking away. So how do you get rid of that heat? Well, you could air condition the room. And so you're going to use some of your energy to keep the room cool. But what the designer of the system and the installer did was to build an aluminium wall, which is actually the external wall of the building. So that aluminium wall there is a massive heat sink to dissipate heat from the back of the inverters, where the heat sinks are, straight out passively to the environment. So, yeah, great idea. Now, I threw this one in because things have changed with 5139. ASNZS 5139, as I talked about yesterday, for those who managed to find the Manageable Mondays live stream, which actually is now on my channel, so you can actually watch it. If you didn't manage to see it live, it's on my channel, YouTube. Just search for Smart Energy Lab. And what's changed is the requirement to have a protection from the spread of fire. Now that house, it's not just that the wall is combustible, but on the other side of that wall, if there was a habitable room, you'd have to have a fire barrier extending 600 mils wider and 1200 mils above around that Tesla Powerwall. The other consideration is you have to have a metre of clearance in front of the battery if it's a path to exit. And that looks like, to me, that's the veranda. May well be stairs at this end where the photograph's taken from, and so the customer would have to walk past that to leave the building. So in the case of a fire caused by the battery system, it could impact on their ability to escape. So those two things would make this system no longer compliant, but otherwise, when it was installed, looks great, and I'm sure the customers are very happy with it. It is on a timber floor, so that would also have to be fire rated too. So maybe some cement sheeting, sending 600 mils wider than the battery. This is a bit of an old one too, and I know this installer, he does beautiful work, and he probably curses that he ever sent me this picture, but I just like to compliment on his workmanship. But there's one small problem, and I'm sure he never does it again. And it's the fact that there is a battery isolator that HRC fuse switch above the vents of a lead-acid battery. And there's an exclusion zone in 4509 which says 500 mils horizontally and 100 mils below the vent is an exclusion zone. So you get your tape measure out, and from those green caps, which are the vents, 500 mils horizontally and up to the ceiling, no ignition points. Like HRC fuse switch is definitely an ignition point. So that's a small problem. This is a construction photo, so just be aware that the batteries were put into a cabinet, but during the construction phase it was photographed. It's a system in Melbourne, a residential system, actually quite a very big for its day hybrid system. But there's a slight problem to do with ventilation on this one too. I mentioned that the cover is on this battery system, and even though they're sealed batteries, you have to consider that batteries vent, even sealed batteries, small amounts of hydrogen. That hydrogen's going to only go up. And see the conduits coming up out of the battery case go straight up onto the switchboard. In fact, I think one of those conduits is almost over the vent. So really it'd be a case of having those entries for those conduits lower than the vents on the battery, or seal those conduits with glands so you're not providing a path for hydrogen. I think this is also from Melbourne. Put in the comments if you know where this one is. Someone sent me this picture. This says to me, someone kind of just wants to say, I've got solar. Because the side of the building is probably not the best place to put it. And really, hats off to the installer. That must have been such a hard job to do. But it's a very, very nicely done piece of art, which also happens to be solar panels. I'm not sure what the boxes on the end are for. They've even enclosed the ends of the panels. Maybe the DC isolators tucked away in there. So I call this a bit of greenwashing, really, in the days when companies just wanted to say we have solar, but they didn't actually care how well it worked. I remember helping a friend install a system on airside at Melbourne Airport for one of the biggest freight companies in the world. And we put 2 kilowatts on this roof. It was so big we didn't need barriers. In fact, we could have kicked a football from the manhole and it still wouldn't have got off the roof. It was so big. And they put 2 kilowatts on so it would go in their prospectus. Here we go. The world's most expensive PV power system for a public toilet. So that's from near Alice Springs on the Larapinta Trail. I should say I nominated this for Off-Grid Installer of the Year award in the days when the CEC were giving out those awards for small scale. And well, they probably still do, but I'm not on the judging panel anymore. I nominated this one because I inspected this. Now, the story behind it is, and it's kind of about why when you're designing a PV system, you have to consider all of the factors, a holistic approach. So the system was designed probably by some engineering company who'd never been to the site. Maybe they didn't actually know much about the use of the site, but it really is just servicing some tourists, maybe a dozen tourists a day as they come off the Larapinta Trail and wait for their bus. They want to use a toilet. And so it's got a couple of toilets, a couple of lights, a pump-out wet septic system. So they've got a holding tank and a flush tank. And if you look on the back there, there's a guy who's arrived to fill up the flushing tank with water. So in the driest part of Australia, we've got a water flush system. Because of the holding tank, they need to aerate it to keep it from getting smelly. And I think the consumption of this toilet block, which services about, it's tourist season, maybe a dozen people a day, was 25 kilowatt hours a day. And so they had to build a PV system with no generator backup, so it had to be oversized to make sure it worked, and therefore it runs 2 lights and a circulating system for the septic. This system cost, I think, $120,000 from memory. That wasn't a rip-off in the day because panels were bloody expensive back then. You're paying $15 a watt, and then they all got stolen. So all the panels were stolen, and the installer had to come back and reinstall the PV array. But this time they had to put in a back-to-base radio with sensors on all the modules, just in case anyone tried to steal it again. So if anyone knows the area, it's about an hour and a half from Alice Springs. So the thieves now know they have an hour and a half. Lovely. This looks like aliens have just landed and popped some PV panels on the roof. This is in Canberra, and this is a very innovative mounting system. There is no physical attachment to the roof. This is a self-ballasted system. That means the weight of the panels and the mounting system associated with it is sufficient to hold the panels in place. It's fully engineered. It's on a building that's a new building, so there is a roof warranty. Penetration of the roof would have been a problem. And it also was a leased property, so it means that this could be taken off and moved somewhere else. So that's a pretty amazing system. And if you wonder how it works, because all the modules are tied together by rails, the wind can't lift all of them or any one panel off without lifting all of them. And because of the low profile and angles, they've done studies in wind tunnels to find out the right angles for turbulence, which actually stop the panels flying off the roof. So there you go. And this is in Canberra, not the windiest place. But there are cheaper ways to do self-ballasting. Yeah, that's what I expected to hear from the audience. So yeah, this is a self-ballasted system with bricks, but the problem is the bricks are partially shading some of the cells, so yeah, it probably needs optimizers as well. So let's move on to the bad, and wow. Well, it's still, I don't know if it's still there, but this is in Queensland, I believe. Geez, I'd love to know where some of these were. These are sent to me, these photos, so I didn't take this one. But I believe it's in Queensland or northern New South Wales. And it looks like some lunch tables on the side of the house. And the shading from one array to the other would probably mean that it wouldn't work very well anyway. And some people try too hard. This is my all-time favourite photo of a terrible battery system. And actually, it was my next-door neighbours when I moved here to Murramura Co-op. And it tells a story of what off-grid solar, DIY off-grid solar, used to look like. There was a kind of concept that the more batteries you had, the better it was. And Telstra in those days used to often sell cheaply their old batteries from telephone exchanges. Those batteries in the front row there, it's a 12-volt system, by the way, so do the maths on those 2-volt cells. They were date-stamped 1973, and they were only replaced about 10 years ago, so they'd done a lot of service. What did they provide for the house? A couple of lights inside, and that's about it. They couldn't even run their inverter because as soon as it turned something on, the voltage drop would cause the inverter to shut down. So that's the front door of the house you can see there, and I actually had to move bikes out. The bikes were jammed in between the batteries for parking. So goodbye DIY off-grid solar. Yeah, you can do your best effort to do a nice job, and then the customer kind of messes it up a bit. That's a bit sad. A garage, a Tesla, but anyway, there you go. It's not the installer's fault. They've put a bollard in even. But this one here, it's a little bit low res, I just realised, is sent to me from one of the utilities in northern New South Wales. They went to inspect for a new connection out of a hybrid system, and this is what they found. There was concern about the batteries not being covered in. You might notice all the terminals are exposed. That means if any of those pots don't make it onto the top shelf, they'll be shorting the terminals of the batteries. The inverter's very close to a sink. Yeah, it's just amazing. And under the new standard, that would not be permitted for lots of reasons, including there's a habitable room, and these batteries may not be fire hazard classification 2. So they may have if they don't have V0 cases, they can't even go inside a building that contains habitable rooms. Here we've got, it's like a game show called Pick-a-Box. The picture was taken by the meter reader who came to read the meter, and he kept on finding inverters and batteries, not meters. This is one house, not a block of units. And so it looks a bit DIY, if you ask me, especially when you look at the inverter and an extension cord plugged in there to run some circuits in the house. Those batteries are flooded lead acid. That means they need to be topped up with distilled water. And so someone's got to climb on a ladder and get that little plastic container in the top right there and fill up those batteries. So, and I don't think those B&R boxes are really rated for 60 kilos of lead on a few screws into the wall. Location. This is under a deck. I'm not sure what's above this, whether the deck has a roof over it. It looks like if it was a roof, it would be thin plastic with let the light through. But that inverter, that lovely Selectronic SP Pro, is not rated for outdoors, so any water would void the warranty and cause it to fail. Also, access in case of an emergency is pretty poor. Like, you actually got to stoop and crawl under there a bit, and yeah, a lot of issues. This is actually another one from my next door neighbour. He asked me one day, "Do I have to clean my panels?" And I took this picture and I said yes. And he said, "It's only a little bit of moss." As many of you will well know, that covering the short side of a module, even just a few centimetres, is enough to turn off the whole module. So that moss, which by the way took 25 years to grow like that, they hadn't been touched for 25 years, would have turned off that array. And I think I've already shown you that one. Here we go. Oh, it's a bit tight, isn't it? Trying to get your inverter tangled into your gas services. So that this is not a battery inverter, but I should point out, still you've got clearances from equipment such as gas for electrical equipment. But if that was a battery, you've got to be 600 mils horizontally away from any appliance, including gas bottles, gas meters, etc. So it's getting really ugly, so we're going to wind up in a second. So if you've got any more questions or comments, just throw them into the chat there. This one actually was sent to me while I was giving a presentation in Sunshine Coast, I think, or was it Brisbane? I can't remember. Oh yeah, I was at the Sharks Club, and one of the installers sort of dashed out of the room in the middle of my presentation, and he came back at the end and showed me these pictures, and I said, well, what happened? He said, I just got called by the fire brigade. It wasn't my system, it's just down the road. They just called me. So there you go. It's a commercial system that caught fire. So who knows what the cause was. One of the problems with PV fires is they're so hot, it's very hard to find out what the cause was, because the cause has often been vaporized. And it is really a concern for fire services. They're often having to confront these failures due to poor product, poor installation practice, and they're not necessarily trained in electrical stuff, so they need to know what to touch and what not to touch, and that's something we're actually addressing in the update of 5033, but I can't talk about that yet. Yep, the wind blew this one off. If you can see this, depending on the size of your screen, the legs are still left behind on the roof above or behind the panels, and so they weren't really attached very well. In fact, those tilt legs from memory only had little grub screws. I wasn't involved in this installation, but I've seen this mounting system before. So if you didn't tighten the grub screws up, off she comes. Amazingly, the panels didn't break, but I wouldn't probably reuse them again. And there's another one. Storms can do wonderful things. The weird is where I'm finishing with, because it's just so amazing. This particular one, I've shown this a lot of times, and it's not trying to diss the installer. In fact, it's hats off to the installer for this one. This was, I think, 2007 or 2008. I took these pictures. Oh, no, not this one. It's coming up in a second. But this one also is weird. Like, there's just not a room on the house. Well, we'll make it fit on the garage. We'll make it fit. That's amazing. Get that many panels onto a garage. But this is still not the weirdest one. This is a tracking system in South Australia. Beautiful piece of engineering, by the way. The guy was a civil engineer or mechanical engineer or something, and he built the tracking system. He couldn't find, he wanted to put the panels optimum, and the corner of the house was the north-facing part of the house. So he built a tracker to get the most out of that little bit of north on that corner. But then he had to find somewhere to put the inverter, and it was kind of a heritage-looking house. Didn't want to stick it on the outside, so he found the ideal location directly below the panels. I guess that inverter gets checked a lot, especially by the boys who visit this room. So you'd certainly be able to see what the production is and if there's any earth faults, etc. Yep. That's kind of what that one's all about. Now, this is the weirdest one. This is the one from 2008. Sorry, I got the order wrong. And it's a system that was installed by one of my students who was an electrical engineer. And at the time, there was, the standard was pre-2012, so it was the old version of 5033. He was concerned about getting the best performance for his friend. So this is a system he put on his friend's house, and he did it as a case study actually for his accreditation. And I think it was only like a 1.5 kilowatt system. I think it was about 8 panels, but he wanted it to work as best as possible, and the roof faced east-west. So every single panel is on its own pole with its own isolator. Pretty impressive stuff. In the days when people were still just smashing holes in tiles and kind of gluing them back together, or trying to screw a deck tide onto a tile, he was using proper flashing. So he was way ahead of his time. So using hose here as protection from the cables. So every entry point into the roof has got an isolator on it. That's actually not compliant anymore. You're not allowed to have inter-string isolators, but there you go. And there's a wide shot. It really does look pretty weird, seeing all these panels on little poles on top of this house. But what about the house? I think the PV system is probably the best thing about the house. So it was his friend's, and I did say, look, well, it's looking pretty amazing from the outside, but I'm worried about those poles. Like, what anchors them? I mean, are they just going to wobble and fall over? And he goes, oh, come on, Glenn, I've got a ladder set up for you so you can have a look on the roof. So we got up onto the roof, and that's what he'd built. He built a whole superstructure to support those poles. Amazing, really amazing. Even before people thought about it, he even had all the interior DC cabling and conduit, so you can see it up on the right-hand corner there, in the days when people used to throw conduit into the eave and just hope for the best. So it's actually a really good effort. I can't imagine what the cost of this system was for a 1.5 kilowatt system. So if you're feeling like work's hard these days, imagine trying to do that. Yeah, there you go. So that's the weird, and that brings us to the end of today. So thanks everyone for 2 Minute Tuesday. I'll just jump back to my outage screen, and I'll be back tomorrow for a Wednesday event. So something a bit different. I haven't actually written the content for tomorrow yet, but I'll be here at 3 p.m. for about an hour or so doing the same thing. So for a big shout out to all those Melbourne installers in Metro Melbourne who may not be able to go to work at the moment. I'm just kind of doing this to keep you entertained. But anyway, if you want to watch these or share them with a friend, you can go to my YouTube channel, Smart Energy Lab, and watch them there afterwards. Anyway, thanks everyone. See ya.